and very important part of calculating any numerical result is to have an estimate of the error involved. After all, numerical calculations are not going to be exact. They are not analytical calculations, and it's important that we have an idea about how big the error is. Now, one way to get the error in a calculation is by carrying out a detailed mathematical analysis of this problem. And in a numerical analysis course in mathematics, partly in the last semester's course, you have already learned how to derive expressions for errors in some numerical methods. So we do have estimates or mathematical analysis based estimates of errors in the quadrature formulas, both for the Newton course and for Gauss quadrature. However, the trouble with this is most of these formulas end up being pretty complicated, and we don't really want to waste a lot of time calculating an error or estimating an error. Also, most of these calculations give you bounds on the errors rather than actual estimates of the errors, and sometimes the bounds may be off by a large magnitude. Your theory might say that the error is bounded by 10 to the minus 3, whereas in actual practice it's 10 to the minus 5. So these rather loose bounds make using the mathematical analysis based expressions not a very great idea in most cases. So how else can we do this? Of course, if we know the exact result for the integral, we can find out how far away your estimate is from the exact result, and that will be your error. However, if we really knew the exact value, in most cases we would not need the numerical method at all. We do solve a lot of problems using numerical methods where the exact value is known, but that is more so that we can get confidence in the numerical methods when we check and find that the errors are reasonably small. Yet in real life problems, we will usually not have access to the exact values. So often it is more practical to estimate the error by following these steps. Carry out the quadrature, some quadrature which we are calling Q, and we carry it out for n points. So we get a result which I am calling Qn for the time being. Then we repeat the quadrature, but this time for 2n points. So this gives me Q2n as a result. Now, for any well-designed quadrature formula, if you increase the number of points, if you go from n to 2n, the chances are very, very high that you are going to get much, much closer to the exact value. So Qn is expected to be much closer to the exact result. Sorry, Q2n is expected to be much closer to the exact result than Qn is. So what we will do is we will estimate the error, which is the difference between Qn and the exact value, by using the difference between Q2n and Qn. By the way, since we are going to, of course, use Q2n as an estimate for the actual answer, if we have a more accurate result, why don't we use it? This really is going to give an overestimate of the error anyway. But overestimating the error is fine as long as we are not doing it by too much. So this is the standard strategy followed. You carry out the quadrature for n points, then repeat for 2n points, and the Q2n gives you the result, and the difference between these two gives an estimate of the error. Why do we need an estimate of the error? Well, for obvious reasons. We need to be able to know how confident we are of our result. Also, and this is really very important, we also need to be able to say whether we need to perhaps do the thing again. Maybe the error is too big. Maybe we need to increase the number of points, and so on. So without an estimate of the error, we cannot judge whether the result we are getting is good enough. We will come back to this point later, but for the time being, let's point out one important thing here. For Newton-Cotes quadrature, this is actually a pretty practical thing to do. After all, when you are dividing your interval into two endpoints, the endpoints that you used earlier, you are essentially putting a point in between, and so all the endpoints that you used earlier are being used for Q2n again. What that means is you do not really have to evaluate the function 3n times, n times for Qn and 2n times for Q2n. We can actually use the function evaluations for Q2n with appropriately chosen weights. Just not don't use the intermediate ones for Qn and so on, and end up with the whole calculation wrapped up. So you don't need to evaluate 3n times, just 2n times. So we have got an estimate of the value and the error with only 2n evaluations. But for Gauss quadrature, which often is better, for the similar n is definitely better, as we saw, there is no such luck with Gauss quadrature, because after all, for Gn, we need to use the nodes, we need to evaluate the function at the nodes of the nth order Legendre polynomial, and for G2n, we need to evaluate them at the nodes of the 2nth order Legendre polynomial, and P2nx and Pnx have no common nodes whatsoever. So this is the hard part. P2nx and Pnx using them together, or rather G2nx and Gnx, if you want to use them, you have to do the calculation. You have to evaluate the function separately for each of the 3n points. So G2n and Gn requires a total of 3n function evaluations. You cannot reuse the points that you have used for G2n to calculate Gn. And this yields a result which is exact up to degree 4n minus 1, because that's what G2n does for you. Now, with 3n function evaluations, we could have carried out G3n at the same computational cost, just 3n function evaluations, slight at different points, of course. So instead of carrying out G2n and Gn, we could have carried out G3n, which would have been exact for polynomials up to degree 6n minus 1. But the trouble there would be, this would give me no estimate about what the error is. So unless you are very confident that your function is well estimated by a polynomial up to degree 6n minus 1, carrying out G3n instead of G2n and Gn ends up being a bad idea, because you have no clue how bad your final result is. So any steps that you might take to correct things if things are going bad will not be available to you. So no error estimate. Now, this is rather surprising. Quite a long time after Gauss had figured out his Gauss quadrature, in the 1960s, Alexander Kronrod from Russia discovered a rather strange and wonderful result. He saw that he could choose n plus 1 new points to the n points already used for Gn. So he got 2n plus 1 points in total, out of which n points were the n nodes of Pn. The other n plus 1 points had to be chosen by using some other mathematical technique. So what Kronrod found was that with these 2n plus 1 points, and by using a new set of weights, not the weights that were used for Gn, of course, there were n weights for Gn, he needed 2n plus 1 weights, different weights, not the same ones as were used for Gn, and with these 2n plus 1 points and 2n plus 1 weights, he could estimate a result which we are calling k 2n plus 1, k for Kronrod, which is exact up to degree 3n plus 1. So what Kronrod managed to do was reuse the values, reuse the function values that were already being used for Gn and get a more precise estimate of the integral. So now instead of Gn G2n, that is using both evaluating G for n points and 2n points, the Gauss-Kronrod quadrature rule becomes Gn k 2n plus 1. And this needs 2n plus 1 function evaluations because the points at which the function is being evaluated for the Kronrod part, k 2n plus 1, include the n points that you need for the Gauss evaluation. So the functions have to be just evaluated 2n plus 1 times. You have to weight them differently, use different number of them, use all of them for the Kronrod, use roughly half of them for the Gauss quadrature, and then this returns an estimate for the integral, which of course is the one we are going to use as a more precise value, which is k 2n plus 1. Also an estimate for the error, which is the difference between k 2n plus 1, the more precise value, and the less precise value Gn. So just to give an idea about the number of evaluations involved, G10 K21, this is a very common Gauss-Kronrod procedure. This is called 1021 procedure or 1021 Gauss-Kronrod quadrature. This requires 21 function evaluations, of course. And this gives you a result which is precise for polynomials up to degree 3n plus 1, in this case 31. Now, using Gauss quadrature only, if we did not use Gauss-Kronrod, then to get to polynomial which is exact up to degree 31, we will need G16. So only 16 function evaluations. That looks less than 21. But remember, if we just evaluate G16, we will have no clue about how big the error is. So to get an error estimate, we need to carry out the pair G8, G16. So the result G16 will have comparable accuracy as the G10 K21. But now the number of function evaluations you need is 8 plus 16. Remember, for the Gauss-Kronrod case, the 21 Kronrod nodes include the 10 Gauss nodes. But for G8, G16, G8 and G16 have to be evaluated at entirely different points. So you need 24 function evaluations. 3 more. 3 may not seem like a lot, but remember 2 things. Firstly, it may be very difficult to evaluate the function itself. So 3 extra function evaluations may add a lot to the computation time. But much more importantly, we may need to keep on repeating the calculation if the error is too big. So the same Gauss-Kronrod procedure may have to be repeated over and over again. And depending on how many times you need to repeat the procedure in order to get to the accuracy you want, this difference of 3 at each step might end up being a huge difference. Now, let me point out that this is basically laying the groundwork for what is actually done in professional numerical integration. We do not use fixed endpoint quadrature. What we usually use is what is called adaptive quadrature. So for this you need an estimated error. No matter which quadrature you are using, whether you are using Gauss-Kronrod or Gauss or Newton codes, you need an estimate of the error. And as I said, Gauss-Kronrod is more efficient than Newton codes and gives an estimate of error with less work than Gauss-Gauss. So that's the one which we usually use for adaptive quadrature. If the estimated error is too large, so we have some idea about how big an error we will tolerate. We usually have that idea depending on what application we want to use this integral in. And if the estimated error turns out to be much bigger than that, what we do, instead of calculating the integral over the entire interval, we now split the interval into two pieces, carry out the quadrature on both pieces along with corresponding estimates of the error, which are bound to get smaller as the interval becomes smaller, and add up the two errors to get the final error estimate. If that is too big, repeat. That means halve the two intervals again to get four intervals. Again carry out the quadrature. So if you are using Gauss-Kronrod, carry out Gauss-Kronrod on each one of the four. Estimate the errors, add up the errors to get the estimate of the total error. If that's too big, repeat, and so on. Keep on repeating until the error becomes within your tolerance level. So you keep on repeating as necessary. So the most common thing that we use in adaptive quadrature is adaptive Gauss-Kronrod quadrature. For the reasons that we pointed out before, Gauss is more efficient than Newton codes, simply because same number of function evaluations end up giving you usually much more accurate quadrature rules, and Gauss-Kronrod works better than Gauss-Gauss quadrature simply because it cuts down on the number of function evaluations needed per step. And in adaptive quadrature, you need to repeat the step several times. And this is implemented, for example, in the quad routine in scipy.integrate. We are going to talk about the scipy module of Python, in particular about the integrate and the ODE int submodules of scipy. It is obvious from the names that they essentially talk about how to integrate things numerically or solve ordinary differential equations. So we are going to talk about how to use the submodules later, but what is important here is that the quad routine in scipy.integrate, and in fact the quadrature routines available in most packages, in most programming languages, actually use adaptive Gauss-Kronrod quadrature.